Okay, this problem says explicitly produce with proof a ring R with unity having a free left module M with the following property. M has a non-trivial R module N that is not free. Okay, so essentially we need a free module with a submodule that's not free. And it's worth noting that actually it's true for PIDs, submodules of free modules are free. So for looking for an example, we have to look to non-PIDs. Many examples are possible, but the easiest are going to involve viewing R as a module over itself. Um, so here's one example we can do. Let R equal Z adjoin X and let M be R, so Z adjoin X as well. So we're viewing R as a left R module. And okay, well, so for a ring with unity, it's always going to be a free module. Um, a ring R with unity will always be a free R module, because what's the basis? Well, it's the identity element. So M is a free the it's the one that is to say the multiplicative identity. Then M is a free R module because it has a basis, namely set containing one. Right, so every um that's gonna span R, and it will also um it's also linearly independent, right? Every element of R can be written uniquely in the form R times 1. Okay, so what's our non-free submodule? Um, so let's let N be the ideal generated by 2 and X. Okay, so note that N is an ideal of R, and hence a submodule of R over itself. Right? If you view R as a left R module, then the ideals of R are the submodules of R. Um, so let's suppose we want to show that N is not free. So we have to show it can't have a basis. Well, suppose that N had a basis consisting of at least two distinct elements, N1 and N2. Okay. Well, then at least one of N1 and N2 would be non-zero. Can't both be zero since they are distinct. And yet we would have n2 times n1 plus negative n1 times n2 equals 0, right? So either n2 or negative n1 would be non-zero, right? Since um, and this would contradict that n1 and n2 were linearly independent, right? Uh, because we've uh, written 0 as an R linear combination of n1 and n2 where the scalars are not all 0. Um, so what does this say? Well, this says that any basis of the ideal generated by 2 and x would have to have only one element. Um, but we know that the ideal generated by 2 and x is not a principal ideal, or we could show that separately. In the adjoint x. That's important, right? If we were in, uh, um, for example, if we were in Q adjoint x, then it would be a principal ideal because it would just be the whole ring itself. Um, uh, so since this is not a principal ideal, it can't have a basis consisting of only one element, because if it did, then it would be principal. So it cannot. So therefore, N is not a free module. Um, okay, good. So, um, one thing that's worth noting is that we're not using the Dummett and Foote definition of a free module here. The Dummett and Foote definition of a free module is uh, not exactly equivalent to the standard one. I guess it's equivalent uh, if the module is not the zero module, not the trivial module. But but otherwise it's probably better to think about um, free modules as a module that has a basis, meaning linearly independent, uh, and generates or spans um, the module, the free module. Um, right, because Thumb and Foot have this weird thing where they say that uh, for every non-zero X has a unique representation. Um, and uh, we so we're just using the more convenient definition. Um, they are equivalent as long as you assume that F is not the zero module. And then the other thing that we should do for completeness is that we should also show, justify this claim that the ideal generated by 2nx is not a principal ideal in Z adjoint X. Perhaps this would be maybe not expected to do here, but let's do it anyways. Okay, so this is sort of a claim that we used. And the claim is um, to the ideal generated by 2nx is not a principal ideal in Z adjoint X. And the proof of that is, well, suppose it was. So suppose it were principal, then it'd be generated by some polynomial or some polynomial A of X in the ring Z adjoint X, ring of polynomials with coefficients in Z. Um, well, 2 is in this ideal generated by the polynomial A of X. So there has to exist some polynomial, call it P, such that 2 is equal to A of X times P of X. So if 2, which is a constant polynomial, is the product of two polynomials, then since uh, Z is a integral domain, um, uh, the um, degree is additive. Um, right, and the degree of a product of two polynomials is the sum of their individual degrees. So the degrees of A of X and P of X are both, they must both be zero since they're uh, the sum of their degrees has to be zero since their product has degree zero. Uh, so they are constants, i.e., we must have, since their product is two, we must have uh, well, constants in the ring Z adjoint X are the only um, way we can have constants multiplying to two, or as if A of X and P of X are elements of the set plus or minus one, plus or minus two, right? Now, if A of X is the constant polynomial plus or one, or the constant polynomial negative one, which is a unit, then the ideal generated by A of X would have to be the whole ring. Um, but that's a contradiction because one, in particular, one is not in the ideal generated by two and X. So that means that a of x would have to be plus or minus 2, would have to be in the second case. Um, but also, we have that we're by what we suppose for contradiction, that x is in the ideal generated by a of x, which implies that x is equal to a of x times some other polynomial q of x, um, for some q of x in z adjoint x. Well, I'll rewrite this since we're saying a is plus or minus 2. It's plus or minus 2 times q of x for some q of x in z join x. Uh, but if q has integer coefficients and we're multiplying all of them by plus or minus 2, then in particular, we cannot get something that has an odd coefficient or just has 1 as a coefficient in this polynomial, right? We can't have x as plus or minus 2 times some polynomial with integer coefficients. So this is also a contradiction. Okay. Again, that's sort of an aside um, from the main thing, but it does fully justify that problem. Um, but as we said, any example of a submodule of a free module that is not uh, free would have to be a non-PID, but we could also just be worse and make it not even an integral domain. So another example would be like, let R equals Z mod 6Z and let M be the same, and then let N be like the ideal generated by 2. And then again, we would have a linear dependence relation um, in, right? So N is like 0 to 4, right? And um, uh, we could write um, so no matter how we try to choose a basis, um, there will always be because there's zero divisors here, there will always be a ways to write uh, zero uh, that don't involve just taking the scalar being 0 from R, right? So like no matter how we try to choose a basis from this set, um, well, you can write 0 as uh, the 0 combination of those elements, or you could do 3 times whichever elements you from the set that you decide to choose, 3 times each of those, and that'll also give you 0 because it kills all of each of these. And so when you add them, you also get 0. And then you have again, um, uh, you again have that they will not be linearly independent. Um, if as long as you choose 2 or 4, you would get that it spans n. Okay. So this is more than enough to say about this problem. Another example that we could give, though, just for completeness, you could say let R be, say some field join x, y, let n be that as well, right? Uh, Viewing R as an left R module, it'll be a free module because the basis will be the identity. But then we can take n as the ideal generated by, say, x and y. And you um, can argue similarly that that is not a free module. So there are lots of ways that this problem could be answered. And we'll conclude there.